So today too, I want us to see something very, very, very essential in our daily life. We normally use systems of linear differential equations, but we ask ourselves, what is it about? It's very, very, very necessary in our daily lives. And once again, I use this opportunity to tell all my subscribers that if you find this um, tutorials to be of good to you, can please inform some of your colleagues or your friends to like or subscribe. Okay, so so today I want us to solve or see something about systems of linear differential equations. Okay, so we will analyze the terms. Okay, when we say system, what is systems? What do we even mean by linear differential equation? What do we even mean by systems? And what do we even mean by linear differential equations? Okay, so from SHS, we all learned systems in terms of biology, or in the field of biology, when you want someone to define a system for you, a system is just a combination of two or more organs to perform a specific task, yeah, or it's a group of organs that work together to carry out a particular task. Okay, so in differential equations, systems is related. I'm relating it to biology. So unlike as we've already said, it's a group of organs that comes together. So here the organs are dependent variables. Okay, so the organs here are dependent variables. So the dependent variables come together. Okay, they come together in various forms to give us a specific task. Okay, so what we are trying to mean is that system can be linear, it can be non-linear, it can be partial differential equation or ordinary differential equation. So whenever we say systems in differential equation, just notice linear or non-linear or partial or ordinary. Okay, so we are for our level we are only interested in the linear and the ordinary differential equations. Yeah. So, so we won't bother ourselves with the partial differential equations and okay, and then non-linear. Okay, so quickly we know that um for a system or for a differential equation to obey a linear or to behave as a linear differential equations, there should be some conditions that should be what satisfied. Okay, so as we move on, I'll mention some of the conditions that should or that for a particular differential equation or a particular differential equation to be considered as a linear or a linearity. Okay, so this is example or some of the example of a system. Okay, so here I can say the dependent variable is my x and the independent variable is the t. Okay, so d square x dt square plus e exponent t dx dt plus t minus 1 x is equal to 0. Okay, so we should know that for this system all the conditions, that's the linear ordinary differential equation, because we can all see it's an ordinary differential equation. Why am I saying that? Because the independent variable, which is the t, is constant throughout, it's not changing. It's so we can define an ordinary differential equation as where there is a series or there is a particular differential equation where the denominator, okay, in simple terms, the dependent variable, which could be x, y, z, or any variable. That's the dependent. Should depend only on one single independent variable. So here, you know that it is only depending on the t. Yeah, so it's an ordinary differential equation. And let's see, is it linear? Yes, it's linear because and these are the conditions. For linear differential equation, the degree should be 1. There shouldn't be no transcendental function written in terms of the dependent variable. 3. No product of the dependent variable and its derivative. Okay, so we can say the dependent variable is x, and it is no transcendental function is written in terms of the dependent variable. Here, the transcendental function could be logarithm, exponential, or trigonometric functions. And here we have only the exponential function, which is e exponent t, but it's not written in terms. It is not written in terms of the dependent variable, because you know that the dependent variable dv, that is the dependent variable, is x, and the iv, which is the independent variable, is t. So that condition is satisfied. The degree should be 1. We can say the degree is 1. Yeah, although the order is, yeah, is 2, but the degree is 1. Okay, so it qualifies to be a linear differential equation. And then lastly, no product of the dependent variable and its derivative. And we can clearly see that there's no product of the dependent variable and its derivative. Okay, so there's no product of the dependent variable. Here, the dependent variable is x, as I said earlier on. The x multiplying t minus 1, the t minus 1 is t is independent. Yeah, that's it's not a dependent or variable. Okay, so that's it. So it's a few recap of a linear differential equation, and that will make us understand well with systems of linear differential equation. Okay, so I wrote this example. This is a system, some example for a system of linear differential equations. Okay, so like y prime prime of t plus a1 y prime prime of t, a2 y prime of t plus a3 y of t is equal to f of t. So we, upon saying that all this condition is satisfied because the degree is 1, all this they are having a degree of 1, because remember a degree is the power to which the order, mm, the order, the highest order, or the order is raised to. Here we know that what is the order of this differential equation. The order is 3. That's the highest, 3, but the degree is what, 1. Okay, so you should take note on it. Okay, so the all the dependent variables, so I wrote this one for our understanding, that say x, y, z are written in terms of the independent variable t. So in systems of linear differential equation, that's what you should know. So anytime you have a dependent variable, say x, y, or z, they are all written in terms of the t. So for example, when you have x prime is the same thing as dx dt. Okay, so it is written in terms of the independent variable t, which is the dt. So y prime 2b is dy with respect to independent variable t, and the z prime 2 is dz with respect to dt. Okay, so for example, this is some of the example of a system of linear differential equation. X prime plus y prime minus 2z prime plus 2x minus 3y plus z is equal to t. So okay, so all the condition is satisfied, and also um the dependent variable, which is the x, y, and z. Okay, so you see, there are numerous variables. So in here we are having x in there, we are having y in there, we are also having z in there. Okay, so the dependent variable can be changing. Okay, so x changing with respect to t, y changing with respect to t, and the z to changing with respect to t. So I said it is we are mostly looking at an ordinary differential equation for our level and a linearity. Okay, that's why we've made this statement a systems of linear differential equation. So systems of linear ordinary differential equations, but they eliminated the ordinary differential equation. So we are for our stage we are just looking at the ordinary differential equations. Okay, so and we've known that the ordinary differential equation, the dependent variable can be changing. So here the dependent variable is x, y, z. It's changing, but it is with respect to only one independent variable, which is t. Note. Okay. Okay. So thank you very much.